This idea of abstraction is actually frequently used when writing up algorithms because, well, let's face it, hardware and software can be very complex. There are things that may be available in one piece of machine or some software that might not be available in some other machine. So we need to take this high-level view. So for example, we can think of memory as just this high-level entity, this single unit, and we don't have to worry too much about the details. But in reality, that's not the case. Memory is a lot more complicated than that because you can think of it as an array of cells that store stuff. So whenever we store something, the hardware is responsible for figuring out exactly where in memory do we store that. We don't specify that in our algorithms because we don't have to worry about that part. We'll let the machine take care of that. So when we're writing these algorithms, we'll use abstraction when we want to try to think of it from a high level approach and not worry about the implementation. Usually what I always tell students is we're separating the what from the how. So when we're trying to write these algorithms, we're thinking about what it is that we want to do. What do we want to do to solve this problem? What steps are we going to take? The how portion will be taken care of when we get to the implementation part of it. So the what takes care of the high level stuff, what it is that we want to do. How we go about doing those steps is going to depend on the programming language we're going to use. It's going to depend on the operating system we're going to use. It's going to depend on the resources that we have available. So we'll worry about those details when we actually get to the coding portion. So this whole approach of separating the what and the how is known as a top-down design. So we come up with the high-level steps, and then we'll break down some of these steps even further. And we can even do that with our algorithms. We may take a high-level step in our algorithm, and then we may break that step down into more detailed steps in a second algorithm. I mean, eventually we're going to have to describe each of these high-level abstractions, and we're going to have to break them down into available algorithmic primitives. It's just that our initial algorithm may not necessarily have it, but when we address these high-level steps, they will be broken down into more detailed steps. For example, let's take a look at the step where we said to compare the respective characters in the text and the pattern to see if we have a match. We just said in one line that we'll do that, but okay, how do we go about doing that? So here's an algorithm that will take care of it for us. So we'll first set the value of I to 1, and then we'll have another variable called mismatch, and we'll initialize it to no, saying that at this point we have not encountered a mismatch between the pattern and the portion of the text that we're starting with. So then we have a while loop that says while I is less than or equal to m, so we haven't gotten to the end of the pattern yet, and mismatch is no, so we haven't determined that there's a mismatch, we're going to do steps 4 through 7. So in step 4, we're going to check to see if the respective characters match. So we're looking at pi, and then this tk plus I minus 1, that's just giving us the appropriate character in the text that's lined up. Remember we saw some examples earlier of how we have our pattern lined up with our text. So k plus I minus 1 is the exact position in our text that we want to compare the respective character in our pattern. So if they're not the same, then we know that we have a mismatch. The pattern does not match the text at this spot. So that's why at step 5 we would say set mismatch to yes. Now, if the condition is false, so if they do match, then we're going to go to step 7 and we're going to increment I by 1, which allows us to go to the next character and compare them. So then we would go back to our while loop and check. Are we at the end of the pattern? If not, do we have a mismatch? If not yet, then we're going to repeat steps 4 through 7 to check the next character in our pattern with the next character in the text, and we just keep repeating this until we get out of the loop. Now, what about the part when we say if there's a match, we'll say something? How do we check if there's a match? Well, we'll check it at the end of that loop. So we go through our pattern and our text and comparing the characters, and after that loop, we can clearly tell whether or not there's a match. And we'll use our mismatch variable. So if mismatch was yes at that point, then that means there was not a match. If mismatch is no, then that means that all the characters lined up, so we can say there was a match at position k. Now, regardless of whether or not there is a match, we still need to increment k by 1 because we need to make sure that we shift our pattern over to the next spot so then we can check to see if there was a match at that place. The last question we need to ask is, when do we actually stop? Because we had that loop that said go until we get the end of the text. So when are we actually at the end of the text? Well, you might think, well, when we get to the last character of the text, we're good, right? But my claim is we don't really need to go to the very last character. I mean, we could, but what's going to happen is our pattern's going to go beyond that, and obviously there isn't going to be any matches there, so that's just kind of unnecessary. My claim is that the last possible character position is actually n minus m plus 1. You might think that seems like a really odd number when you think about it. Well, here's how we can go about this. It's not as difficult as you think. So our pattern has m characters. So when we go to the mth position in T, from this spot, we would be at position m. At position n, I want to make sure I clarify that. Position n, not m. Now, you might think, well, wait, how? How do we do this? Okay, let me show you a quick example. So let's say I have P1, I'll put it up here. So there's position 1 for our pattern, P1. And so I'm saying that the last possible position here would be T n minus m plus 1. Okay, now we're going to go all the way to position Pm. Well, how many spots did we go? Well, we went m minus 1 characters from P1. So what's m minus 1 characters from Tn minus m plus 1? Well, if we take, we're basically doing m, I'll put this down here because we're running out of spots here. So we're saying n minus m plus 1, and we're going to go m minus 1 spots. Well, what is that? Well, the minus m and plus m cancel out, and the plus 1 and minus 1 cancel out, so that comes to n. So that means that the position here is going to be Tn, which just happens to be the last character of our text. So what we're saying here is that we can just go up to Tn minus m plus 1. I apologize for the handwriting if it's a little difficult to read. But after this is the last one we need to check. Afterwards, we don't need to shift our pattern anymore. So here is the final complete algorithm. So if you remember before, we had some high-level steps here that had some details missing. Now we went ahead and addressed those and added them back into the algorithm. So this gives us a full 18-step process, which is a little bit longer than what we've seen before. But let me tell you, some of these algorithms are much larger than this. But this gives you an idea of what we're doing. So the first 3 steps are initializing our size, the text, the pattern, our k. And then we have this big while loop from steps 4 all the way to 17. So notice our condition is a little bit different. So k is, so we have here, k is less than n minus n plus 1. So that takes care of our position, because we said before that the last position would be n minus n plus 1. So we set the value of I to 1. We handle our mismatch. So we are doing our character matching in this section right around here. So that takes care of comparing one character at a time. So once we're done all that, we get out of that loop. And then this area here will take care of checking the whether or not we have a match or not. So if mismatch is no, then we're going to print that we do have a match at position K. And otherwise, we don't do anything. We don't need to print that there was no match. We just say there was a match at this position. Then we increment K by 1. We'll go back up to the loop, and we'll just do the whole thing again. And then once we get to the end of our text, or in this case, once we get done with the iteration where K is n minus n plus 1, we can say that we're done.